Hi, class. Okay, why is there a lady who seems to be giving a graduation speech to a bunch of cheetahs? Why is this happening? Anyway, Chapter 5, the binomial probability distribution and related topics. So, just a little introduction here. Everything we've done so far, chapters 1 through 4, has all kind of seemed a little different. And the reason for that is all of that is building on what we're going to be seeing for the rest of stats. So, what we did in chapters 1 through 4, you may have seen in the past. You may have seen in other math classes or even just things you know, like probability. You deal with that uh, on your own. So, things like that, you are building on itself. You are taking those things and now you're going to build on it, and that's going to be the rest of stats. But everything we see from here on out is going to be using what we've seen before in class and using that to give us more of what we're looking for. So, in the first 4 chapters, you were able to use previous knowledge to help you. Now, we're just using knowledge we've learned so far. So this stuff is going to get much more difficult and make much less sense. You really gotta strive through it and work really hard at this stuff to be able to understand what we're going through. So work hard and good luck. The learning target for today is to be able to calculate mu and sigma, mean and standard deviation, for discrete distributions and linear combinations. For the scale, 3, you can calculate mu and sigma for discrete distributions and linear combinations. 2, you can calculate mu and sigma for discrete distributions or linear combinations. 1, you can determine the difference between discrete and continuous variables. And 0, you cannot determine the difference between discrete and continuous variables. Let's get started. Section 5.1, Introduction to Random Variables and Probability Distributions. Focus points. Distinguish between discrete and continuous random variables. Graph discrete probability distributions. Compute mu and sigma for discrete probability distributions. Compute mu and sigma for a linear function of a random variable x. And compute mu and sigma for a linear combination of 2 independent random variables. Random variables. For our purposes, we say that a statistical experiment or observation is any process by which measurements are obtained. For instance, you might count the number of eggs in a robin's nest or measure daily rainfall in inches. It is a common practice to use the letter x to represent the quantitative result of an experiment or observation. As such, we call x a variable. So x is whatever you're looking for. Like if you're counting eggs in a robin's nest, maybe you're looking for 2 eggs or 3 eggs or 4 eggs or 7 eggs. X represents whatever number of eggs you're looking for. A quantitative variable x is a random variable if the value that x takes on in a given experiment or observation is a chance or random outcome. A discrete random variable can take on only a finite number of values or a countable number of values. We're not really going to get into the difference between finite and countable, but it'll make sense what discrete is in a moment. And a continuous random variable can take on any of the countless number of variables in a line interval. The distinction between discrete and continuous random variables is important. because of the different mathematical techniques associated with the two kinds of random variables. So, if we use the examples we were just looking at, eggs in a robin's nest, those are discrete. You're dealing with 0, 1, 2, 3, 4. You can't have half an egg, or that's not the kind of thing you're looking for. A half of an egg wouldn't matter in this case. A continuous random variable would be the other example. Rainfall in inches. You can have half an inch, or 0.1 of an inch, or 0.01 of an inch, or 0.001 of an inch, or 0.0001 of an inch, or so on. So that's an infinite range that you can pick from. It's continuous. In most of the cases we will consider, a discrete random variable will be the result of a count. The number of students in a statistics class is a discrete random variable. Variables such as 15, 25, 50, and 250 are all possible. However, 25 and a half students is not a possible value for the number of students. Most of the continuous random variables we will see will occur as the result of a measurement on a continuous scale. For example, the air pressure in an automobile tire represents a continuous random variable. The air pressure could in theory take on any value from 0 pounds per inches squared, psi, to the bursting pressure of the tire. Values such as 20.126 psi, 20.12678 psi, and so forth are possible. Probability distribution of a discrete random variable. A random variable has a probability distribution whether it is discrete or continuous. A probability distribution is an assignment of probabilities to each distinct value of a discrete random variable or to each interval of values of a continuous random variable. So we're assigning probabilities for every value. I'm getting lots of emails. Features of the probability distribution of a discrete random variable. 1. The probability distribution has a probability assigned to each distinct value of the random variable. And 2. The sum of all the assigned probabilities must be 1. Dr. Mendoza developed a test to measure boredom tolerance. He administered it to a group of 20,000 adults between the ages 25 and 35. The possible scores were 0, 1, 2, 3, 4, 5, and 6, with 6 indicating the highest tolerance of boredom, meaning they could take boredom a lot well. They don't get bored as much as people with, say, a 0. The test results for this group are shown in this table. So each store and then how many people stored each level. And there were 20,000 total subjects. If a subject is chosen at random from this group, the probability that he or she will have a score of 3 is 6,000 out of 20,000. Notice in the table before, 3 was 6,000 people did it out of 20,000. Or 0.3. In a similar way, we can use relative frequencies to compute the probabilities for the other stores. So these are now the relative frequencies of each store. Each store is our x that we talked about. So the probability of x happening for each store. These probability assignments make up the probability distribution. Notice that the stores are mutually exclusive. No one subject has 2 stores. The sum of the probabilities of all stores is 1. The graph of this distribution is simply a relative frequency histogram. See figure 5.1, in which the height of the bar over a store represents the probability of that store. So we learned about relative frequency histograms back in chapter 2. So again, here is an example of something we did previously. So the relative frequency histogram shows the probability of each of these. Probability that you could get a 0, a 1, or 2, so on the test. Since each bar is 1 unit wide, the area of the bar over a store equals the height and thus represents the probability of that store. Since the sum of the probabilities is 1, the area under the graph is also 1. The top-notch clothing company needs to hire someone with a score on the boredom tolerance test of 5 or 6 to operate the fabric press machine. It must be really, really boring to do that. Since the scores 5 and 6 are mutually exclusive, the probability that someone in the group who took the boredom tolerance test made either a 5 or a 6 is the sum. Probability of 5 or 6 is probability of 5 plus the probability of 6, which we learned last chapter. We want 5 or 6, so we add them. 0.08 plus 0.02 is 0.1. Notice that to find the probability, we could have simply added the areas over the bars, over 5 and over 6 from the relative frequency histogram. 1 out of 10 of the group who took the boredom tolerance test would qualify for the position at top-notch clothing. A probability distribution can be thought of as a relative frequency distribution based on a very large n. As such, it has a mean and standard deviation. If we are referring to the probability distribution of a population, then we use the Greek letters mu for the mean and sigma for the standard deviation. When we see the Greek letters used, we know the information given is from the entire population rather than just a sample. If we have a sample probability distribution, we use x bar and s respectively for the mean and standard deviation. The mean and standard deviation of a discrete population probability distribution are found by using these formulas. Mu is equal to the summation of x times p of x. Mu is called the expected value of x. It's what we expect to get. Sigma is the square root of the summation of the squared deviations from the mean times p of x. Sigma is called the standard deviation of x, where x is the value of a random variable. P of x is the probability of that variable, and the sum is taken for all the values of the random variable. Note, mu is the population mean, and sigma is the underlying population standard deviation, because the sum is taken over all values of the random variable, i.e. the entire sample space. The mean of a probability distribution is often called the expected value of the distribution. The terminology reflects the idea that the mean represents a central point or cluster point for the entire distribution. Of course, the mean or expected value is an average value, and as such, it need not be a point of the sample space. The standard deviation is often represented as a measure of risk. A larger standard deviation implies a greater likelihood that the random variable x is different from the expected value mu. So, the larger the standard deviation, the more that it varies, the more that the number will be away from what we expect. So if we want it to be what we expect, we want a low standard deviation. Are we influenced to buy a product by an ad we saw on TV? National Infomercial Marketing Association determined the number of times buyers of a product had watched a TV infomercial before purchasing the product. The results are shown here. So, if they saw it 1 time, 25%, 2 times, 31%, 3 times, 18%, 4 times, 9%, and 5 times, 15%. Note it says 5 is actually 5 or more, but it's actually going to be 5 for this example. We can treat the information shown as an estimate of the probability distribution because the events are mutually exclusive and the sum of the percentages is 100%. Compute the mean and standard deviation of the distribution. We put the data in the first two columns of a computation table and then fill in the other entries. So knowing how to do this table is very important. So first we have our x's, 1 through 5. Then we have the probabilities that they gave us, probabilities of each to happen. Then we find x times the p of x. So it's just x times p of x in each one. 1 times 0.27, 2 times 0.31, and so on. Then we have the deviation from the mean, x minus mu. So, and then we calculate that. Then we have the deviation squared, so we just take this number and square it. Then we have the deviation squared times the p of x, so we take this number and multiply it by p of x, and we get these numbers. Then we take the summation of x p of x to find our mu, our expected value, which in this case is 2.54, and we find the variance, which is 1.869, by adding up all these. The average number of times a buyer views the infomercial before purchase is 2.54, sum of column 3, as we just found. To find the standard deviation, we take the square root of the sum of column 6. So we add up all of column 6, that gives us the variance, and then to find the standard deviation, we just take the square root of that. So the square root of 1.869, which is 1.37. Linear functions of a random variable. Let a and b be any constants and let x be a random variable. Then the new random variable L equals a plus bx is called the linear function of x. Using some more advanced mathematics, the following can be proved. Let x be a random variable with mean mu and standard deviation sigma. Then the linear function L equals a plus bx has mean, variance, and standard deviation as follows. Mu sub L, or the expected value of L, or the mean of L, is a plus b times mu. Sigma squared sub L, or the variance of L, is b squared times sigma squared. And sigma sub L, or the standard deviation of L, is the square root of b squared times sigma squared, which is also the absolute value of b times sigma. Linear combinations of independent random variables. Suppose we have two random variables, x sub 1 and x sub 2. These variables are independent if any event involving x sub 1 by itself is independent of any event involving x sub 2 by itself. Sometimes we want to combine independent random variables and examine the mean and standard deviation of the resulting combination. Let x sub 1 and x sub 2 be independent random variables, and let a and b be any constants. Then the new random variable w equals a x sub 1 plus b x sub 2 is called a linear combination of x sub 1 and x sub 2. Using more advanced mathematics, the following can be proved. Let x sub 1 and x sub 2 be independent random variables with respective means mu sub 1 and mu sub 2, and variances sigma squared sub 1 and sigma squared sub 2. For the linear combination w equals a x sub 1 plus b x sub 2, the mean, variance, and standard deviation are as follows. Mu sub w, or the mean of w, is a times mu sub 1 plus b times mu sub 2. Sigma squared sub w, or the variance of w, is a squared times sigma squared sub 1 plus b squared times sigma squared sub 2. Sigma sub w, or the standard deviation of w, is just the square root of the variance. Let et sub 1 and et sub 2 be independent random variables with respective means mu sub 1 equals 75 and mu sub 2 equals 50, and standard deviation sigma sub 1 equals 16 and sigma sub 2 equals 9. So we're taking these and going to use them in some examples. Let L equals 3 plus 2 sub 1. Compute the mean, variance, and standard deviation of L. L is a linear function of the random variable sub 1. Using the formulas with A equals 3 and B equals 2, we have our mean, standard variance, and standard deviation. So now we can just plug them into the formulas we found a few slides ago. So just plug them in and we get 153, 1024, 32. If you're not sure where the formulas came from, just go back a few slides and plug those in. It's just simple plug and chug. Notice that the variance and standard deviation of the linear function are influenced by the only coefficient et sub 1 in the linear function. Now let w equal et sub 1 plus et sub 2. Find the mean, variance, and standard deviation of w. W is a linear combination of the independent random variables et sub 1 and et sub 2, using the formulas both a and b equal to 1, because there's no numbers in front of either, et sub 1 or et sub 2. So we have, and again, it's just plug and chug for the mean, variance, and standard deviation. Plug them into the formulas for w. Now, let w equal et sub 1 minus et sub 2. Find the mean, variance, and standard deviation of w. W is a linear combination of the independent random variables et sub 1 and et sub 2. Using the formulas with a equals 1 and b equals negative 1, because it was a minus, we have, again, plug and chug for the mean, variance, and standard deviation. And finally, let w equal 3 et sub 1 minus 2 et sub 2. Find the mean, variance, and standard deviation of w. W is a linear combination of the independent random variables et sub 1 and et sub 2 using the formulas with a equals 3 and b equals negative 2. We have, and plug and chug once again. So the difference between all those is noticing when a and b are 1, one of them is negative 1, or you've just got a and b being numbers other than 1 or negative 1. Plugging them in and seeing what happens. Now time for the sponge. Use the following table and give me the expected value and the standard deviation. You're going to have to use the table we set up in the video and be able to find mu and sigma. That's it for the lesson. Once again, please make sure to take notes on the entire lesson. Attempt the sponge. Rate yourself on the learning target and scale. Make sure I can see that. After you do all that, take a picture or a video of your notes, submit them all to Google Classroom, and have a good night.